Right, I'm going to go over the Edexcel Physics Triple 2021 Paper 2. It's higher tier. You get 1 hour and 45 minutes and it's worth 100 marks. Question 1, Part A. A student gives a plastic strip an overall electric charge. Part 1. Describe one way that the student can give the plastic strip an overall electric charge. Well, use friction. It's always the same answers. So basically, rub the rod. If it was worth 2, you'd say that makes the electrons transfer. Part 2. Figure 1 shows a gold leaf electroscope that can be used to investigate static electricity. The electroscope has no overall charge. The gold leaf has a very small mass and can bend very easy. That's this little gold leaf here. It's like a Kit Kat wrapper with a bit of metal. The student brings a negatively charged plastic strip near to the cap of the electroscope. The gold leaf bends away from the metal rod. Which diagram shows the way that electric charge is now distributed? Right, so you're bringing a negative rod toward the plate. Now you're not even touching the plate, but what you're going to get is induced charge. So the negative charges will repel away other negative charges, and what that's going to do is it's going to leave positive charges behind. So the answer is C. These negative charges would have started up the top here. So this overall charge at the top would have been 0 at first. Part B. Figure 2A shows another gold leaf electroscope that has been given an overall negative charge. A student connects the metal cap of the charged electroscope to earth with a piece of wire as shown in Figure 2B. Explain why the gold leaf has moved. Right, so basically that was negative and that was negative. Now all those negative charges are going to come along here, they're going to move up and they're going to discharge down to earth, and then basically that gold leaf isn't getting repelled anymore. That's why it's gone back to being flat against the metal rod. Electrons move and get discharged to earth. The gold leaf is no longer repelled, because they did ask why the gold leaf's moved, so I thought I'll just pop that in. Yeah, don't need to put those things in the brackets, you'll actually get the marks just for putting those top 2 things. Part C. 2 small objects P and Q are each given an electric charge. Figure 3 represents the electric fields around the objects P and Q. So P is going in and Q, the charges are coming out. Use information from Figure 3 to give 2 differences between the charge on P and the charge on Q. Well, the charges always come out of the positive, so that must be a positive charge, and the charges go into the negative. And you can also say that the charges on here must be bigger because the lines are closer together. It's the same for an electric field, which is what this is, as it is for a magnetic field. When the field lines are closer, it means that it's a stronger field, which must mean that this charge is greater. So charge Q is bigger because the field lines are closer, which means the field is stronger, and P is a negative charge and Q is positive. Part 2. Object P and object Q are held near to each other so that their electric fields interact with each other. State the effect that the electric field of object Q has on object P. Well, they are opposites and opposites attract. Object Q will attract object P. Question 2. Part A. Figure 4 shows the results from an experiment where the potential difference, which is the voltage, across a filament lamp was varied. The current and the voltage were measured. Right, there's a current voltage graph. Part 1. Describe the relationship between the current and the voltage as shown in the graph in figure 4. 2 marks. Easy peasy. As the voltage increases, the current is increasing and it's a curve, so you say it's non-linear. If it was a straight line, either up or down, you would say it's linear. But because it's a curve, it's non-linear. Part 2. Use the values of the voltage and current at point P and at point Q on the graph in figure 4 to complete the table in figure 5. Right, let's have a look at that graph. At point P, the voltage is 1 and the current is 20 milliamps. So at P, the voltage was 1 and the current was 20 milliamps. And point Q, off barnacles, right, do the little dotty lines going down like that. That's voltage is 3.5 and the current is about 44 milliamps. So 3.5 and 44 milliamps. Now, because you're flicking from one page to another, make sure you don't mess up the voltage. Part 3. Calculate the resistance of the filament lamp when the voltage is 4.5 volts and the current is 51 milliamps. Use the equation. That's kind. We don't even need to rearrange it. So the voltage was 4.5 and the current is 51 and that's milliamps. So stick a times 10 to the minus 3 on the end to turn it into amps, because there is 1,000 milliamps in an amp. And that comes out as 88.2. And that'll be ohms. And they've just done theirs to 1 decimal place, so we'll just do ours to 1 decimal place. Part 4. Explain why the resistance of the filament lamp changes as the voltage across it increases. Right, let's go back and have a look at the graph. Right, on a current voltage graph, if the gradient is steep, that means the resistance is small, and if the gradient gets flatter, that means the resistance is getting bigger. So the gradient is steep here, so that means the resistance is small, and the gradient is flatter here, which means the resistance is big. So basically the resistance is increasing, and the reason that is because bulbs get hot, and that means that there's going to be more collisions between the current trying to go down through the wire and the ions that make up the wire. So let us show you how to write that. Resistance increases as the bulb gets hot So there's more collisions, increased collisions of electrons with the ions. So basically, inside the wire, it's made of copper ions, if it's a copper wire, so they're all positive. And then you've got your little negative electrons. Now when it's cooled, these ions don't vibrate very much. So there's not many collisions, so the resistance is small. As the wire gets hotter, these ions start to vibrate more because they've got more kinetic energy. Now when the little electrons try to go down through the wire, there's a lot more collisions. And collisions is basically the resistance. So the resistance gets big. Question 3, Part A. Describe in terms of particles 2 differences between a solid and a liquid of the same substance. Right, so basically in a solid compared to the particles in a liquid. So the particles in a solid are closer together. These particles are in nice neat rows. So you could say the particles in a liquid are randomly arranged, and the particles in a solid can only vibrate. Whereas in a liquid, they can actually move. Any 2 of them. Part B. Figure 6 shows the dimensions of a solid block of concrete. Density of concrete rho equals 2100 kilograms per metre cubed. Calculate the mass of the concrete block. Use the equation. Great. They've even rearranged the equation for us. So we're looking for the mass. Just need to pop the density in. So that's 2100, and that's kilograms per metre cubed. Right, I'm just going to scroll down a little bit. They want the mass in kilograms. We need to multiply that by the volume. Now you'll get the volume by doing the height times by the width times by the length. And that equals 630, and that'll be kilograms. Now just be careful in case any of these readings are in centimetres. You would have to convert it into metres, just to make sure that those metres cancel out with those metres, just to leave kilograms behind. Question C. Figure 7 shows a shed made mostly of concrete blocks. State 2 practical ways to reduce heat loss from the shed. Right, well, from any building you lose heat from the walls, you lose it from the door, you lose it from the windows, you lose it from the roof, and you also lose heat from the floor. Right, so from the walls, how do you reduce heat loss? Cavity wall, which is basically a wall on the outside, then a little gap, and then breeze blocks on the inside. And this little gap here is the cavity. Remember, if you go to the dentist's with a gap in your tooth, that's a cavity. Right, the door, how do you reduce heat loss? You need a draft excluder. The floor, you can put some carpet or some underlay, or some foam if you've got laminate flooring. Windows, double glazing. Roof, fiberglass. Loft insulation. So put any two of those down. Part D. On a very cool day, the temperature of the air is -4 degrees C. Calculate the value of this temperature on the Kelvin scale. Right, to work out the temperature in kelvins, you take the temperature in degrees C's and you add 273 to it. So you'll have -4 degrees C plus 273, and that equals 269, and that'll be kelvins. Remember, if you need to convert it into temperature in degrees C and it gives you the temperature in kelvins, you need to take away 273. So if you had 273 Kelvin, take 273 away from it. That basically would equal 0 degrees C. Question 4. Part A. Figure 8 shows some water in a tank. Part 1. The bottom of the tank has an area of 0.8 metres squared. So that's area. The force on the bottom of the tank due to the water is 2,400 newtons. That's our force. Calculate the pressure due to the water on the bottom of the tank. So pressure is our target. And pressure equals force divided by area. Let's just pop the numbers in. 2,400 newtons divided by 0.8 metres squared, and that equals exactly 3,000 newtons per metre squared. And remember, 1 newton per metre squared equals 1 Pascal. So they want the answers in pascals, which is basically just newtons per metres. Don't let that put you off. So that's just 3,000 pascals. Part 2. More water is added to the tank. Explain how the pressure on the bottom of the tank changes when more water is added to the tank. Well, if you're adding more water in here, you've got all that extra force pushing down. And pressure equals force divided by area. So the area stayed the same, but the force got bigger. That'll make the pressure get bigger as well. More force from the water, so bigger pressure. And you should always base your explanation on the calculation as I showed you up the top. Part 3. Figure 9 shows an object on the bottom of the tank of water. Draw an arrow on figure 9 to show the direction of the force exerted by the water on the surface of the object at point X. Right, the force always acts perpendicular, which means at 90 degrees. So that arrow there is what you need to draw. There would be force right the way down here as well. It would all be at 90 degrees. If it was across here, that would be at 90 degrees there as well. The way they might change that question is they'll say you've got a water balloon and you pop it. Which way does the water come out? Well, the water would always come out at 90 degrees to the surface as well. So just in case they change it for you for this year. Part B. Figure 10 is a graph showing how the atmospheric pressure changes with the height above sea level on the Earth's surface. That's the height getting bigger. That's the atmospheric pressure up here. Part 1. An aeroplane descends from 6,000 metres to 2,000 metres. Use the graph to find the change in atmospheric pressure as the aeroplane descends. Easy peasy. So at 6,000 metres, you can see the pressure is 50 kilopascals, and at 2,000 it's 80 kilopascals. So the difference was 30. And because it's gone from 50 to 80, that's definitely a positive change. If it said it was flying from 2,000 to 6,000, then that would have been minus 30. So just watch for that. Part 2. Suggest one reason why the atmospheric pressure is greater at 2,000 metres than at 6,000 metres. Right, if this is the Earth, as you get higher in the atmosphere, there's less and less air as you go higher. So when you're up there at 6,000 metres, that's why it's only 50 kilopascals, perhaps. And when you're lower, at 2,000 metres, there's a lot more air. So that's why the pressure is bigger, 80 pascals. Remember, pressure is caused by the particles hitting the object. So the lower the height, the atmosphere is more dense. So basically more air particles. If you keep going high enough, you'll get into space and there's no air particles. So the pressure would go right down. Question C. Figure 11 shows two drawings of the same person on a bed. Explain why the person exerts a different pressure on the bed when standing up than when lying down. Right, base your explanation on the calculation. Pressure equals force divided by area. Right, look at the size of the area there. That is a big area. So his force is getting more spread out. So big area, the force ends up getting spread out, so the pressure is small. Whereas this chap, the area is small. He's got the same force pushing down, because it's the same person with the same weight. Pressure equals force over area. If the force is the same, but the area is now smaller, that makes the pressure get bigger. When standing up, pressure is bigger because the area is smaller, so the force is more concentrated. And it would be the opposite if you'd said lying down. When lying down, the force is spread out over a larger area, so the pressure is smaller. Either say that or that. Hope that helps. Question 5, Part A. A student uses plotting compasses to investigate the magnetic field between the poles of two bar magnets. Figure 12 shows one of the plotting compasses and one of the bar magnets. The student places the two magnets on a piece of paper with a pole of one magnet a few centimetres away from the pole of the other magnet. The student places 20 plotting compasses on the paper near the magnets. Figure 13 shows the direction in which each of the plotting compasses points. Part 1. Draw two rectangles on figure 13 to show the positions of the two bar magnets. Label the north pole and the south pole of each magnet. I've had to read all of that and it's only worth 2 marks. Are they having a laugh? Right, so what they're saying is that this magnet is part of the setup down here, and so is this. So if I grab a hold of that and I kind of pull that down, where can I put this so that it seems to make sense? Right, well, I think about there. So what do we know about magnets? Well, we know that the magnets, or magnetic field, if we follow the compasses, sort of make a line, don't they? Like a butterfly effect around the magnet. Now that would seem to make sense because it would be going like that, and it would be going like that. And then if we had another magnet over here, then that is going to be a sort of similar pattern, whoops, on this side. And remember, the magnetic field comes out of the north and goes into the south. So it's going in, that must be south, that's coming in, so that must be south, and then that'll be north, and then that'll be north. So the magnetic field will be coming round like that. Just got a bit excited there. That's better. So there you go. A little bit of a tricky one. I haven't saw that many times over the last 27 years. So someone's trying to come up with clever ideas. I don't think it's a very good question personally. Edexcel should get in touch with me and I'll write a few questions for them. Part 2. The student wants to determine the shape of the magnetic field for a larger area around the magnets. Describe how the student should continue the investigation using just one plotting compass. Right, so I'm sure you've done this at school. You basically put your magnet in the middle of the page and then you put your little plotting compass on one end of the magnet, and the little plotting compass should point out to the north and go into the south, remember. Now if you do a little dot where that north's pointing and then move the compass there, it'll start to come round here, put another dot there, put your compass there, it'll point there, do a little dot, and if you keep on doing that, putting a little dot and then moving the compass next to the dot, it should go round like this. And there you are. Then what you'd do is you'd connect all of those dots together, and then you'd know the shape, and also the compass shows you the direction of the magnetic field. If you did that on both sides, you'd end up with your lovely magnetic field pattern that looks a bit like a butterfly. Right, how to say that for 3 marks. Here we go. Place a compass on the paper near the north pole of the magnet. Put a dot at the end of the compass needle. Move the compass to the new dot. Repeat. And then join the dots to show the shape and direction of the magnetic field. I mean, to be honest, that could be worth 5 or 6 marks. Part B. Two long, thin magnets are held with their north poles facing each other. The force F between the magnets can be calculated using the equation F equals K over D squared, where K is a constant, D is the distance between the magnets. Part 1. The magnets are 4 centimetres apart. The force between the magnets is 1.2 newtons. Calculate the value of K and state the unit. Right, so we're going to need to rearrange the formula to get K. So we'll use a magic triangle. K is on the top shelf out here, so it goes on the top shelf in here. And then I've got 2 spaces and 2 things. Shove those things in those spaces and cover up what you're looking for. We're looking for K. What are you left with? F times by D squared. So that's how you work out K. K equals F times by D squared. Pop the numbers in. 1.2 newtons times by 4 squared. And that equals 19.2. Now that 4, the units was centimetres, and because it's being squared, that turns it into centimetres squared. So we've basically multiplied newtons by centimetres squared. So it's 19.2, and that's newtons centimetres squared. Now I taught A-level physics for 20 years, and what we used to encourage the students to do is put a little dot in there. Just means that times by that. Remember, if it was that divided by that, you'd put this little slash line in, but that was not right. Part 2. The magnets are held the same distance apart, but with the north pole of one magnet now facing the south pole of the other magnet. The value of K does not change. State how the force would compare with the force in part 1. So in part 1, the magnets were held with their north poles facing each other. So they were like this. Right, well they'll be repelling. Then they're going to change one of them round. So now the south is next to the north. One of the north poles is now facing the south pole of the other magnet. So that's going to attract. The force will be equal in size, but opposite in direction. In other words, it's going to attract rather than repel. It's only worth 1 mark. You'll definitely get the mark. And if I was you, I would cross out what you don't want the examiner to consider. So that was our thought processes, but we don't want the examiner to think that that's what we still think. That was what was happening in part 1. Question 6. A student investigates moments of forces. Figure 14 shows the apparatus used. The pivot is under the centre of the rod. A magnet is fixed to one end of the rod. A piece of modelling clay is fixed to the other end of the rod. The system is in equilibrium. Now that means it's balanced, like a nice balanced seesaw. Part A. State the relationship between the moment of the weight of the magnet and the moment of the weight of the piece of modelling clay about the pivot. Well, if it's in equilibrium, that's the weight of the magnet, and that'll be the weight of the modelling clay. Now this will be causing, if you follow the force, the weight, go round the back of the pivot and keep on going, then that is going to be an anti-clockwise moment. And if I do the same on this side, follow the weight down, follow the force down, go round the back of the pivot and keep on going that way, that is going clockwise. So that will be a clockwise moment. And if it's in equilibrium, the anti-clockwise moment will equal the clockwise moment. So that's basically your answer. For 1 mark. Part B. The student fixes a coil to the bench under the magnet as shown in figure 15. The coil of wire is connected to a DC power supply so that there is a current in the coil. To bring the system back into equilibrium, the student hangs a 0.05 Newton weight on the rod 8.4 centimetres away from the pivot as shown in figure 15. Calculate the size of the force between the magnet and the coil. Right, so that weight is basically going down that way, and then this will be getting attracted to come down that way. So if we call that force 1, and then we'll call this one force 2. This will be distance 2 to go with force 2, which means this will be distance 1 to go with force 1. And if they're in equilibrium, again, we need to have this anti-clockwise moment equal the clockwise moment. Remember, the moment is the force times by the distance from the pivot. So that force times by 12 centimetres will equal this force times by 8.4 centimetres. So if we rearrange that, F is going to equal 0.05 times by 8.4 centimetres all divided by 12 centimetres, and that equals 0.035 newtons. You didn't have to convert the centimetres into metres. As long as they're both centimetres on both sides, they'll end up cancelling out to leave just the newtons. Part C. Describe how the student could develop the investigation to determine if the size of the force between the magnet and the coil is directly proportional to the size of the current in the coil. Right. If you measure the size of the current and you measure the size of the force in the way that I've just showed you in the last question, then what you would do is move the weight and turn up the current to re-establish equilibrium. Then if you re-measured the current and the force, now there's a couple of things you can do from here. You could either get the ratio of force divided by current for each reading. If the ratio is the same, then they're directly proportional. The other thing you could have done is, once you've done these steps here, you could then just plot a graph of force against current, and if you get a straight line through the origin, then you know it's directly proportional. Plot force against current. If you get a straight line through the origin, it shows the relationship is directly proportional. A little bit tricky, that one. Never saw that question too many times over the years. Part D. The student reverses the direction of the current in the coil. Describe how the student can bring the system back into equilibrium without making any changes to the magnet. Right, let's have a little look and see what's going on. Right, so if they reverse the current, that'll reverse the magnetic field. So at the moment, there's an attraction. If you reverse the current, there's going to be a repulsion, which will push that up. So what you'll then have is a clockwise moment created by the magnet. So then you will have to move this weight to create an anti-clockwise moment. Now the way you'll do that is to move this weight onto this side of the pivot. Remember, follow the weight down, go round the back of the pivot, keep on going, and you'll see that is anti-clockwise. So then this would create the anti-clockwise moment in order to balance out that clockwise moment. So I'll show you how to write that. Move the weight to the other side of the pivot. Actually, you could take some of that mass of the modelling clay away, but you'd only get 1 mark for saying that, so you're better off saying what I've just said. Question 7, Part A. 2 cyclists ride on a hilly road and go through points P, Q, R and S. The diagram in figure 16 shows how the vertical height of the road changes during the journey from P to S. Well, there's the vertical height there. Part 1. The greatest overall change in gravitational potential energy for each cyclist is between which 2 points on the journey? Right, so remember, gravitational potential energy equals mass times by gravity times by height. So the difference in GPE will be the difference in the height, because the mass and the gravity will be the same. So when was there the greatest height change? Well, between P and Q, it went from nothing to 20, so that's 20. Between Q and R, that goes from 20 to 35, so that's 15. And between R to S, it went from 35 down to 10, so that's 25. So from R to S is the biggest change in height, so there'll be the biggest change in gravitational potential energy. So the answer is D. Part 2. The total weight of one cyclist and bicycle is 700 newtons. Calculate the total amount of work done against gravity when the cyclist travels from point P to Q in the journey. So from P to Q, the difference, or the vertical height that travelled, was 20 metres. Now work done, remember, equals energy transferred, which equals force times by distance. So the force was 700 newtons. And we're doing it against gravity, so we need the vertical height, which, as I've just said, was 20 metres, and that comes out as 14,000, and that'll be joules. Part 3. The gravitational potential energy of the other cyclist changes by 11,250 joules when travelling from point Q to R. Calculate the mass of this cyclist. So M is our target. Gravitational field strength is 10, so that's G. Use the equation. Change in gravitational potential energy equals mg delta H. So let's pop it in a magic triangle to rearrange it. M times by G times by delta H goes on the bottom. Delta GPE goes there. We're looking for the mass, cover that up. What are we left with? Delta GPE divided by G times by delta H. And they're going from Q to R. So let's just have a little look. So from Q to R was 15 meters. So the change in gravitational potential energy was 11,250 joules. Divide that by 10 newtons per kilogram and multiply that by the 15 meters. And that equals 75 kilograms. Part 4. Explain why the total amount of work done by a cyclist between points Q and R is different from the change in gravitational potential energy of the cyclist between points Q and R. So going from Q to R, you will gain gravitational potential energy. So in going from Q to R, you will gain gravitational potential energy. However, the amount of gravitational potential energy you gain won't be as much as the work you had to do to go up, because you will always lose some energy as heat, or some of your work done will be to overcome air resistance, and that'll get transferred, as I say, to heat to the environment. So work is done to overcome air resistance or friction. So just say you gained 1,000 joules of gravitational potential energy. It might have took you 1,200 joules of work to get you to the top of the mountain. So in other words, 200 joules has been wasted to overcome friction, air resistance. It's just kind of turned into heat and it's been lost to the environment. I hope that makes sense. Yeah, that would go into efficiency then. So remember, efficiency would equal the useful energy out divided by the total energy in, and then multiply it by 100 if you want it as a percentage. So in other words, in this particular example here, we got 1,000 joules useful out of gravitational potential energy, because we can use that energy again as we descend, but we had to put 1,200 joules of energy in. So that would be like 83% efficient. Now everything in red plus this bit here is just me trying to explain things to you. Don't actually write that as the answer for part 4. You'll always waste some energy as heat to the environment. Part 5. The cyclists lubricated the chains and the wheel bearings of their bikes before setting off. Lubricating the chains and the wheel bearings helps too. Well, it would help to increase the efficiency of the cyclist and the bicycle. So, in other words, we're looking to decrease that value there, the amount of work that you've had to do. So that was the wasted energy. If we have lubricated the chain and everything, it might only take 1,100 joules. So, in other words, we've only done 100 joules of energy has been lost to overcome air resistance and friction. So now we could get the efficiency. Useful energy out divided by total energy in, and that would equal 91% efficient. Part B. The kinetic energy of another cyclist is 2,800 joules. The mass of the cyclist is 85 kilograms. Calculate the velocity and use that equation. Right, well, we need to rearrange it. So let's do our magic triangle. So a half times by mass times by velocity squared goes on the bottom, and that would leave kinetic energy to go on the top. Now we're looking for the velocity, so cover that up, and what you're left with, velocity squared would equal kinetic energy divided by a half times by m. Now remember, we don't want velocity squared, we want velocity, so let's square root both sides, and would be left with v equals the square root of kinetic energy divided by a half times by m. Right, let's pop the numbers in. 2,800 joules was the kinetic energy. Divide that by a half times by the mass, which was 85 kilograms. And that equals 8.1. And that's meters per second. Question 8. A technician investigates different electrical devices that are used in a car. The technician connects a device to the 12-volt car battery. The technician measures the current in the circuit and the potential difference, which is the voltage, across the device. Figure 17 shows the car battery and the device that is being tested. A Part 1. Draw on Figure 17 to show how the circuit should be completed so that the current in the circuit and voltage across the device can be measured. Right, well, you need an ammeter to be placed in series with the device, and you need a voltmeter to be connected in parallel across the device. You could either put your voltmeter here, or you could sort of put your voltmeter over there. Part 2. The technician tests a headlamp. The current in the headlamp is 4.8 amps, so that's our current I, when connected to the 12-volt battery, so that's our voltage. Calculate the power, so that's P, supplied to the headlamp. So power equals current times by voltage, so that's basically 4.8 amps times by 12 volts, and that equals 57.6 watts. Part 3. The technician tests an interior light. The current in the anterior light is 600 milliamps, right, so that's 600 times 10 to the minus 3 amps when connected to the 12-volt battery. So 12 volts. Calculate the energy transferred to the interior light in 7 minutes. Now remember, you've got to convert that into seconds, so that'll be 7 times by 60, because there's 60 seconds in a minute. So that's 420 seconds. You never leave anything in minutes. Use an equation selected from the list of equations at the end of the paper. Right, so we've basically got, we're looking for E, and we've got the current, we've got the time, and we've got the voltage. So basically, Emmerdale is on ITV. So the energy is the current times by the time times by the voltage. So that's 600 times 10 to the minus 3 amps multiplied by 420 seconds multiplied by 12 volts, and that equals 3024, and that'll be joules. Part B. The technician connects 4 devices to the car battery. Each device is connected to its own switch and its own fuse. Figure 18 shows how the 4 devices, fuses and switches are connected. The current in each device is shown next to the device. So the headlamp uses 4.8 amps, interior uses that, heaters that, and radios that. Part 1. Calculate the current in the wires to the battery when all the devices are switched on. Right, so all of that is basically going to come together and it just needs to be added up, and that's how much will be going through here. So the total current will equal 4.8 amps plus 600 times 10 to the minus 3 amps plus 10 amps plus 2.3 amps, and that equals 17.7 amps. Part 2. State how the overall resistance of the circuit changes when any one of the devices is switched off. So voltage equals current times by resistance. Therefore, resistance equals the voltage divided by the current. If you keep the voltage the same, but you decrease the current, that's going to make the resistance increase. And as I say to my students, base your explanation on the calculation. And also make sure you can rearrange equations. Otherwise you're going to lose easy marks. Part 3. There is a current of 2.3 amps in the radio when the radio is working correctly. Which of these should the technician choose to protect the radio circuit? So 2.3 amps in the radio, how to protect the radio circuit. Right, you always choose a fuse that is slightly higher than the normal operating current. So the normal operating current is, that's working correctly, 2.3. So we need to go higher than 2.3, but not too high. So the next one up from 2.3 is 5 amp fuse. So we'll use that one. Part 4. Explain why the wires to the battery in a car are thicker than the wires that connect each device to its switch and its fuse. Right, thicker wires have got a lower resistance. So that basically means they can carry more current without getting hot. So less energy will be wasted as heat. I would say that one and that one. But if it was worth 3, I'd say that one as well. If it was worth 4, I'd go with that one. Question 9. Part A. There is an alternating current of 3 amps in the primary coil of a transformer. There is an alternating current of 6 amps in the secondary coil. The transformer is 100% efficient. Part 1. The size of the potential difference voltage across the secondary coil is... Right, basically the current, so there's the primary coil, there's the secondary coil. The current was 3 and it's gone to 6. So if the current has doubled, that means the voltage will have halved. So whatever happens to the current, the opposite thing happens to the voltage. So this is obviously a step down transformer. So there'll be more coils on the primary than the secondary. So your answer is D. The size of the potential difference across the secondary coil will be half the size of the voltage across the primary coil. Part 2. Explain how an alternating current in the primary coil causes an alternating current in the secondary coil of the transformer. Right, so here's your basic transformer. That's your primary coil. That's your secondary coil. Now an alternating current in the primary coil creates an alternating magnetic field in the primary coil. Now this is an iron core, which of course is magnetic. So the alternating magnetic field in the primary coil is carried across and cuts through the coils of the secondary coil. And that creates an alternating current in the secondary coil. Well, remember, what came first, the chicken or the egg? We're not sure. But what comes first, the voltage or the current? The voltage. So technically, before the alternating current is induced, an alternating voltage is induced, which creates the alternating current. 1, 2, 3, 4, 5. That might even get you 6 marks if it was a 6-mark question. So that's basically how a transformer works. It has to have alternating current to make it work. Transformers don't work with direct current, DC. Part B. The primary coil of a different transformer is connected to the 230 volt main supply. The voltage across the secondary coil is 15 volts. So that's how many volts goes in, that's how many volts comes out. The primary coil has 600 turns. Calculate the number of turns on the secondary coil. Use an equation selected from the list of equations at the end of the paper. Right, that's the one we want. The voltage across the primary coil divided by the voltage across the secondary coil equals the number of turns on the primary coil divided by the number of turns on the secondary coil. So VP divided by VS is going to equal NP divided by NS. Now we're looking for the number of turns on the secondary coil, so we're looking for that. So what I like to do is I like to get the thing we're looking for on the top. So if we flip this side and we flip that side, then this will still equal this, and we'll have NS on the top. So NS divided by NP will equal VS divided by VP. Now we just need to get NS by itself. So if we multiply both sides by NP, then that NP will cancel out by that NP, and it'll just leave us with NS equals NP times by VS over VP. So NP is the number of turns on the primary, which was 600. Multiply that by the voltage on the secondary, which was 15. And divide that by the voltage on the primary, 230. And that equals 39.1 turns. So that's basically 39. Part C. Figure 19 shows a coil of wire that is being rotated between the poles of a magnet. Right, this is an alternator. You can recognise that because it's got slip rings rather than split rings. So the current goes positive and negative. So the current goes positive, then negative. Figure 20 shows how the current in the coil changes during one complete rotation of the coil. Explain why the current changes in the way shown by the graph in figure 20. Your answer should include details of the position of the coil relative to the magnet at each of the times labelled P, Q, R, S and T. You may use diagrams to help your answer. Right, this is borderline A-level. I taught A-levels for 20 years. A-level physics. Right, let's have a look and see what's happening. Right, let's draw in some magnetic fields. So the magnetic field goes from the north to the south. So the magnetic field will be going that way. Now at point P, you've got 0 current. So that must mean that this coil is not cutting any magnetic field lines. Right, you only get an induced current when the coil is cutting through the magnetic field. If it can cut through the magnetic field, the maximum amount of magnetic field change, that'll create the biggest current. So that would be at point here and down here. So the coil will be horizontal there, like that. And if you've got the magnetic fields like that, then as soon as this starts to move a little bit up and down, it's going to cut through the most number of field lines per second. So you're going to get your maximum current. And if I colour that side of the coil purple and I leave that one blue, down here, your coil will once again be horizontal like that, but it's flipped 180 degrees. So now the purple side's on here. So the current will have flipped as well. Instead of maximum positive, it's going to be maximum negative. And once again, that's the magnetic field lines that's going to get cut. Now at positions T, R and P, the current is 0. So that must mean that the coil is not cutting through any magnetic field. So basically, your coil is vertical. There's your magnetic field lines coming through here. When the coil is spinning like that, it's not actually going to be cutting through any magnetic field lines. So your current's 0. So your coil will be vertical there as well, and it'll be vertical there. If I colour it purple, that'll be purple there. So it's spinning, and then the purple side's there. Then it keeps spinning, so the purple side will be on the top. Then it keeps spinning, so the purple side's on the side. Then it keeps spinning, so the purple side's now on the bottom. Right, so how do we say that then? This is probably one of the trickiest parts of the triple physics, learning about the alternator, and the dynamo's tricky as well. So when the coil moves through the magnetic field, the coil experiences a change in the magnetic field. And that induces a voltage or a current in the coil. So that's the basics. Now the size of the voltage or current depends on the rate of change of the magnetic field. Now the greatest change will be when the coil is moving perpendicular to the field. Let me go back up and show you when it was perpendicular. So it's moving up here and the magnetic field's there. So that is perpendicular. Remember, something's perpendicular when they're at 90 degrees to each other. So you've got the mag field and then you've got the movement. That's perpendicular. And it's the same here. The movement is going up by those red arrows, and the mag field is going across that way. Now let's compare that to these. So the movement is that way, and the magnetic field's that way. So they are parallel. The movement is parallel to the magnetic field. So the voltage you're going to get is 0. And it's the same here. So there's your magnetic field lines. So your movement is that way and your magnetic field's that way. So that's parallel. And your movement's that way and your magnetic field's that way. So that's parallel. Your voltage there is nothing. And that's parallel there. So your voltage there is nothing. Here it was perpendicular. So your voltage and your current will be maximum. And here the movement was perpendicular to the magnetic field. So your voltage is going to be maximum there. But here it's maximum positive and here it's maximum negative. Now if you're thinking there's a lot going on here, is there not a simple way to answer it? Yes, we could basically just analyse how big the voltage is at each point. So basically we've got a maximum current at positions Q and S, and that'll be because the coil is horizontal at Q and S. So that's where you would have the maximum rate of change of the magnetic field at Q and S. The direction at Q is the opposite to S because the currents were opposite. So remember, you had a maximum positive at Q and a maximum negative at S. And we had 0 current at P, R and T. And that's when the coil was vertical at P, R and T. So you decide which way you'd rather go. This way kind of avoids more of the theory. This top part here is more of what the theory is all about. And remember, when the 0 current coil was vertical, that was when the coil and mag field were parallel, and when you got the maximum current, that was when the coil and the mag field were perpendicular. Perpendicular. Right, I hope that helps. Pretty tricky stuff. Question 10, Part A. An electric kettle contains 1.41 kilograms of water at 25 degrees C. The kettle is switched on. After a while, the water reaches boiling point at 100 degrees C. The specific heat capacity of water is 4,200 joules per kilogram per degree C. Part 1. Calculate the amount of thermal energy supplied to the water by the kettle. Give your answer to the appropriate number of significant figures. Use an equation selected from the list of equations at the end of the paper. Right, well that's the mass of water, that's the starting temp, this is the final temperature, and this is the specific heat capacity, which is known as C. Right, let's have a little look. Okie dokie, this is the formula we want. The change in thermal energy equals mass times by specific heat capacity times by the change in temperature, mc delta theta. So delta Q, the change in the heat energy, equals the mass times by the specific heat capacity times by the change in temperature. So we'll just pop the numbers in. 1.14 kilograms times by 4,200 joules per kilogram to make it heat up by 1 degree, multiplied by the temperature change. Well, final temperature was 100, take away the starting temperature 25, and that equals 444,150, and that's joules. Now they want us to do it to an appropriate number of sig figs. Right, well let's go with what they've gave. Right, that's to 2 sig figs, that's to 3 sig figs, that's to 1, that's to 2. Generally I do say do it to the most number of decimal places or significant figures that they have. So personally I would be doing it to 3 significant figures. Now what does the 1 do to the 4? It doesn't do anything to it. So that's just 4, 4, 4, then it'll be 0, 0, 0. So 444,000 joules. I've looked at the mark scheme and they will accept it to 2 sig figs. In fact, that's what they're expecting, but they will still give you 3 marks for 3 sig figs. I suppose maybe it was because that one was to 2 sig figs and that one was to 2 sig figs. So that one is only one number to 3 sig figs. Part 2. The kettle is kept switched on and the water continues to boil. After a while, the mass of the water in the kettle has decreased to 1.21 kilograms. The thermal energy supplied to the water during this time was 450,000 joules. Calculate the specific latent heat of vaporization of the water. Use an equation selected from the list of equations at the end of the paper. Right, let's have a look. Right, there's your specific latent heat. So this is the equation we need. The thermal energy for the change of state equals the mass times by the specific latent heat. So Q equals M times by L. And they want us to calculate the specific latent heat of vaporization. So let's rearrange that. N times by L goes on the bottom and Q goes on the top then. Cover up L, what you're left with, Q divided by M. So L equals Q divided by M. Now, Q is pretty straightforward. It's just the thermal energy, which is 450,000 joules. Right, the mass. So it was 1.41 kilograms of water. And then I've only got the mass of water goes down to 1.21. So basically, 0.2 kilograms of water is turned into steam. So that's been boiled off, that's turned into steam. And the specific latent heat of vaporization is how much mass has changed state. In other words, changed from water into steam. So we need to use the 0.2 kilograms is the mass of steam we've made. And that comes out as 225,000. So 2,250,000 joules per kilogram. That's the specific latent heat of vaporization. So that's how much heat energy you need to put in to get 1 kilogram of the water to turn into steam. Part B. This question is about determining the specific heat capacity of aluminium. An aluminium block is placed in boiling water as shown in figure 21. Right, little piece of string hanging out the side. The piece of string is tied to the aluminium block so the block can be transferred from the boiling water to the cold water. Right, so pick up that string and they're going to dump that block of aluminium into the cold water. 6 marker, by the way. Describe how a student could use this apparatus and any additional items needed to determine the specific heat capacity of the aluminium. Your answer should include how the student would obtain the necessary measurements and use the measurements to calculate the specific heat capacity of aluminium. Right, well, as I say to my students, base your explanation on the calculation. So if we're trying to get the specific heat capacity, the formula will be delta Q equals M times by C times by delta theta. Right, so we need to measure the mass of the aluminium. So we're trying to get the specific heat capacity of the aluminium. Right, let's rearrange that equation to make C our target. So magic triangle, top shelf, need 2 multiplied signs because there's 2 there, and it's M times by C times by delta theta, and delta Q will go on the top, cover up C, and we are left with delta Q on the top divided by M times by delta theta. What you'd normally say is use a joule meter to measure the heat energy provided to the water. So I will still say that, but I'm just going to probably not expect to get a mark for that. So use a joule meter to measure the amount of heat energy provided to the water. So that would be saying you're using a joule meter and you're measuring the heat energy. So ordinarily I would say that gets you 2 marks. So we'd need to know the mass of the aluminium. With what? With a mass-top pan balance. You'd need to measure the starting temperature of the water and the final temperature of the water. Using a thermometer. Now use a stirrer to make sure the temperature is the same everywhere in the water. Then you'd need to calculate the change in temperature by doing the final temperature take away the starting temperature. Now that's what I say to my students is the basics. Now I think you're definitely going to get 1, 2, 3, 4, 5, 6, 7. That's absolutely fine for 7, even without that. Plus you'll get a 1 for saying the equation, that's 8. Now if you want me to explain a little bit more, the way they normally do this experiment is they'd normally say something like they get this water up to 100 degrees C. Now that basically means that this block of aluminium is also going to be at 100 degrees C. Now what you'd need to do is measure the temperature of this water here at the start. Now let's just say it's room temperature, so the starting temperature might be about 20 degrees C or something. Now by the time you pop that aluminium into here, the temperature, the final temperature, might go up to 25 degrees C. So basically the energy that the aluminium has lost would equal the energy that the water has gained. Right, okay, so I can see how we can actually work out that even though they've used a Bunsen burner. So we can work out the heat energy gained by the water if we measure the mass of the water. We have to assume that they let us know that the specific heat capacity of water, I mean, it's always the same. It's 4,200 joules per kilogram to make it heat up by 1 degree C. And we know that I've just said the temperature is going to go to 25 from 20. So we know that the change would just be 5. So technically, that's how we could work out the heat gained by the water. And then that would also equal the energy lost by the aluminium, which would give us this value here. So then as long as we're measuring the mass of the aluminium and the temperature change of the aluminium, which by the way, that aluminium is going to go from 100 degrees C, because that's what it was at the start over here, down to 25 degrees C. So the temperature change is 75 degrees C. They sometimes say how to make it more efficient. Right, you're going to have to try to get that aluminium into this water as quick as possible and as safely as possible without losing too much thermal energy. Transfer the aluminium block quickly so the thermal energy lost is only small. You'd also get marks then for saying measure how much water you've got in this beaker of cold water. I guess you'd have to measure the mass of the beaker and the mass of the beaker and the water. So the mass of the cold water would equal the mass of the beaker and water, take away the mass of the beaker. And I think I've just about covered it there, but to be honest, I would go with this part personally. You'll definitely get the marks for saying that. And that's the last question. So if you've saw the full paper through, well done. I'll definitely increase your grades. Yep, been teaching for 27 years. I know what I'm talking about. I've saw people improve their grades massively by doing loads and loads of past papers. So work hard, be nice. Bye for now. See you in the next video. Want to see more videos like this? Subscribe to my channel, GCSE Physics Explained.